Say, today you're going to learn about polynomial functions.
Today you can look at polynomial functions.
Try that again. Say, today you're going to learn about polynomial functions.
Today you can learn about polynomial. I can't remember what you said.
One more time. Today you're going to learn about polynomial functions.
Today you can learn about polynomial functions.
Very good. All right. Well, there you have it. Polynomial functions. Well, if you're there watching this, that means I'm not there because we had a baby. Or I am there and you're watching this because I don't want to. I put all this work into it and might as well show it to you. But hopefully I'm not there. And no, I don't have a name to tell you yet. Sorry. All right. So we're gonna start chapter 5. And it's all on polynomial functions. So what I've got here is just a Word document that I wrote up. And I'll have this posted up on Schoology. So if I go too fast, you can go back and read through it on here. All right, so all these graphs are polynomial functions. These two should look familiar. Okay, but the rest of these are all polynomial functions. So just based on those, like just what you see right there, you should be able to look at these next couple graphs, these next few graphs here, and determine which of those 4 are not polynomial functions, and have a reason for that. So this graph here on the right, actually both the graphs on the right are not polynomial functions because this one has a sharp corner, and polynomial functions are supposed to be smooth. And this graph here has a break in it, and polynomial functions are supposed to be continuous. So if you want to jot down notes, you can. Otherwise, I mean, this PDF will be up on Schoology, so you don't have to. But key point, the graphs of polynomial functions are always smooth and continuous. So that's one way you can tell a polynomial function just from the graph. So at the end of this lesson, you should be able to identify, write, and classify polynomials. You should be able to understand the patterns between polynomial functions and their graphs. You should be able to identify the end behavior of a polynomial function and identify a polynomial function as being odd or even based on its graph. All right. So here's kind of the main idea. All polynomial functions, in equation form, they all look like this. Like this is the general form, like y equals x, or y equals x squared, or y equals x cubed. But that being said, they can have other terms in it. So they can have all these additional terms, but it's this first term that kind of describes the function. So the standard form is to put the highest degree first and then just go down. So like x to the 5th and x to the 4th and x cubed. The number in front, this a sub n, is your leading coefficient. So that's one of the important parts of the function in equation form. The n is your degree. That's one of the important parts. And then a sub 0 here is your constant term, which is always your y-intercept. So that's one of the important parts of the equation form. So this is just an example. This is a 3rd degree polynomial with a leading coefficient of 1 and a constant term of 32. So this is what the graph would look like. It's just this curvy polynomial function. Okay, so key point. In order to have a polynomial function, at least when you're in equation form, all the coefficients have to be real numbers. So you can't have I, basically. The variables cannot be in the denominator. And then 3, the powers have to be non-negative integers, which kind of says the same thing as number 2, because if you added x to the negative 2, that'd be 1 over x squared, so then you'd have a variable in the denominator. But this also says that your powers have to be integers, so you can't have a half or something like that. And then when looking at the graphs have to be smooth and continuous. So all 4 of these right here are polynomials. They all fit. They'll meet these conditions. Even this last one, which looks a little odd, it's still a quadratic with a leading coefficient of pi. But these 4 are not polynomial functions, just because this one has an x in the denominator. This one has a half as your exponent. This next one is a exponent with a negative, and this last one is an exponent with an x. So, they look similar, but you have to be able to identify a polynomial from the equation, and you should also be able to identify it from the graph. All right, classifying or naming. Usually we name it based on the degree, the highest exponent in the polynomial. So x cubed plus 2x is a third degree polynomial because the highest exponent is 3. We give specific names to some of these, and there are specific names to all of them really, but after we get to a certain number, we just say fifth or sixth degree. So if the degree is 0, it's a constant polynomial. If it's 1, it's a linear polynomial, linear function. If it's 2, it's quadratic. So we just got done with those. If it's a third degree, it's cubic, fourth quartic, fifth is quintic, but you can just say fifth degree, sixth degree, all the way up to nth degree. You can also name or classify polynomials based on just the number of terms. So this is a monomial, 1 term, 2 terms of binomial, 3 terms of trinomial. And again, after trinomial, we just say polynomial. So anything after, and really you could say all of these are polynomials, but when you name them, anything after 3, you just say is a polynomial. Oh, these are supposed to be covered up, but they're not. That's all right. So name these polynomials. This is a 2-term, and it's cubic, so it's a cubic binomial. This is a 1-term cubic, so a cubic monomial. This one, the highest degree is 2, 3 terms, so quadratic trinomial, quartic binomial. And this one, same thing, like you could give it the special name or you could just say 7th degree trinomial. And the last one here is a 5th degree polynomial. All right, so now you should be able to identify a polynomial function in its equation form. You should be able to classify or name them based on, and also know the important parts. So the leading coefficient, the degree, and the constant term. Any questions? Good. All right. The graphs. These are all graphs of polynomial functions, and there's some patterns that we can identify here. Here we go. All right. A constant function has a degree of 0. A linear function, degree of 1. A quadratic function, degree of 2. And we've studied all those already. We're just going to finish the puzzle with all the rest. So cubic, quartic, quintic, 6th degree, 7th degree, 8th degree. And so one thing you should notice, I hope you noticed already, is that as the degree gets higher, the more terms you have. So notice a linear function has no terms. Quadratic function has 1 turn. It's going down, changes direction, now it's going up. A cubic function changes direction twice. So it goes up, changes direction, goes down, changes direction, goes up. So there's 2 turning points on a cubic. There's 3 turning points on a cubic, or on a quartic. There's 4 turning points on a quintic. So the number of turning points is always 1 less than the degree. So that's one key point. The number of turning points is always 1 less than the degree. The other important part that you should identify or notice from all these graphs is the degree also corresponds with how many x-intercepts there are. So we just got done with quadratics. Remember, quadratics always have 2 answers, 2 x-intercepts. Well, cubic equations are going to have, cubic functions have 3 x-intercepts. Their equations have 3 answers. So when we get to solving an 8th degree polynomial, there's 8 answers to that equation. So key points, the degree equals the number of answers, and the degree minus 1 equals the number of terms. And there are some exceptions to this. For the most part, this is true, but I'll explain it a little bit more when I get back. All right. Odd and even functions and end behavior. So I said, simply put, but not quite accurate, even functions have an even degree, and odd functions have an odd degree. But there are functions that are neither odd nor even, and I'll address those in a second. But graphically, even functions always have end behavior, meaning this end and this end. They always end going in the same direction. So that's even functions always end going in the same direction. Odd functions always have end behavior that end in opposite directions. So what you want to look at is, 1, the leading coefficient. If it's positive, it ends going up. And if it's negative, it ends going down. And if it's even, they're both the same. And if it's odd, they're both different. So notice this one is positive, so it ends going up. and odd, so it starts with going down. So it's down, up. This one's negative, so we know it ends going down, and it's odd, so that means it be started going up, so up, down. Graphically, even functions are always symmetric about the y-axis, so you can just fold it over on the y-axis. Odd functions are symmetric about the origin, so right there at the center. But that sometimes it's a little kind of confusing what that means. But to be symmetric about the origin just means that the graph will be unchanged if you flip it over the x and then over the y. So if you were to flip this curve over the x and then over the y, it would land on itself. So that's what symmetric about the origin means. And those are odd functions. This last one here is neither odd nor even because it's not symmetric about the y or the origin. So those are even and odd functions. And we'll look into, later we'll look into how to identify even and odd functions just from the equation. But right now you should just be able to identify them from the graph. Okay, so what we've got here, key point, leading coefficient's positive, it ends going up. Leading coefficient's negative, it ends going down. The degree is even, the ends are the same. The degree is odd, the ends are opposite. In the book and on Khan Academy, it describes it this way. It says, as x approaches infinity, so as x gets larger, y approaches infinity. And as x goes to negative infinity, y goes to positive infinity. So it says, like, what happens if you have an odd function with a leading coefficient that's positive? As x approaches infinity, y goes to positive infinity, y goes up. And as x goes to negative infinity, y goes to negative infinity. So there's that language there you kind of need to know. An example would be to describe the degree and the leading coefficient just from the graph. So the degree, well, the degree, we can count the turning points. We can also count the number of x-intercepts. Now this one's a little, maybe I should have done this one second. In fact, I'll just do this one second. I'll come back to it. Okay, so this one we can see that there's 3 points of intersection, so this is a third degree. And because this thing ends going down in the negative direction, we know that the leading coefficient is negative. All right, so if we were to write the graph of this, we at least know that it starts out negative and it's a third degree. Now this one's not as easy because we have a turning point. We have 1, 2, 3, and really this is like a flattened out couple of turning points. So we have at least 1, 2, 3 x-intercepts. But if you remember, when you're right on the x-axis, that counts as 2. Remember parabolas that were right on the x-axis, that just meant that the roots were the same. So we actually have 2 there. So we have 1, 2, 3, and then 4. But now let's count the turns. So we have 1, 2, 3. And like I said, this one's kind of a flattened out version. So if you imagine this hump kind of coming down and then going back up again, so it actually would turn here and turn here. So we have 1, 2, 3, 4, 5 turns. So 5 turns means that this is a 6th degree. Okay, and the leading coefficient, since it ends going up, so that it ends going in the positive direction, we know that the leading coefficient was positive. All right. The last thing. The last thing is, at least in terms of what's in the book and what I'll be quizzing you on, what you need to know. The last thing you should be comfortable doing is evaluating a polynomial function for a given value. And I already showed you how to do this on the graphing calculators. So let's do this one. It says, find the value of this function when x is -2. So you need to be able to input this function into the calculator. And you can do this by hand. You can just put -2 into the function and find the value, which is fine. But if you have a calculator handy, it's much easier to do it this way. So 5x to the third minus 2x squared plus 10x minus 15. Okay, so we inputted the function. And then it says find the value of this function when x is negative 2. So if you remember, what we can do is we can go to second table set and change auto to ask. So it'll ask us what our input value is. So then we go second graph to go to our table that says what do we want our x to be? We want it to be negative 2. Enter. So when x is negative 2, the y value is negative 83. So we can write it like this, or you can say f of negative 2 is negative 83. All right. So I'll post this up on Schoology. Hopefully it's something that will be useful to you. And now you should be probably getting out the laptops and doing the tasks on Khan Academy. Hope all is well. I'll see you when I see you, maybe next week. All right. See you guys.
If you have any questions, mail my daddy.
Say, no, it's email. If you have any questions, email my daddy.
If you have any questions, mail. I can't remember what you said.
If you have any questions, email my daddy.
If you have any questions, mail my daddy.
All right, there you have it. Email me if you have any questions. Say goodbye.
Bye. Did I get it right?
You did. Good job.